What's up everyone, Dr. J here. In this video I will be continuing the equilibrium theme, but it will be applied to acids and bases. In General Chemistry 1, you were introduced to acids and bases in the form of acid-base reactions, so let's take a quick minute to review the difference between an acid and a base according to the Bronsted-Lowry definition. In this definition, recall that we are following the movement of protons, or H+ ions, from one molecule to another. You learned that acids are proton donors and bases are proton acceptors. For example, dissolving HCl gas in water results in the products of H3O+ and Cl-. The proton from the HCl got donated to the water. Similarly, if the base NH3 is dissolved in water, it results in NH4+ plus OH-. The proton from the water was donated to the NH3. You also learned that acids and bases come in two different flavors, strong and weak. This has nothing to do with how corrosive the acid or base is, rather it depends on the degree of ionization. Let's talk about strong acids and bases first. A strong acid such as HCl will completely ionize in solution. This can be shown graphically. Dissolving HCl gas in water results in the HCl ionizing completely to form H3O+ and Cl-. Strong bases such as NaOH also completely ionize in solution to form a metal cation, in this case Na+, and hydroxide ion OH-. I've updated the graph to show these products. Since both strong acids and bases ionize completely, they are not written as equilibrium reactions, so they only go in one direction and are not reversible. If we take a quick look at the periodic table, note that strong bases are hydroxides of most group 1 and 2 metals, whereas the strong acids are these guys here, the first three being the easiest to remember. Be sure that you can recognize them all. Now, the difference between strong acids and weak acids is that weak acids only partially ionize. Here's an example using acetic acid. If the reaction is represented graphically, you can see that the result of the reaction is that most of the acetic acid remains intact and only a small portion of it ionizes. The same logic is applicable to weak bases such as ammonia. See the updated graph that shows the relative proportions of the reactants and products. Reactions involving weak acids and bases are equilibrium reactions, and this makes them reversible. So think back to the chapter on equilibrium and recall what you learned about the equilibrium constant and how you can determine the relative amounts of reactants and products at equilibrium based on the value of the equilibrium constant. Now, with that, can you determine whether the equilibrium constant for weak acids and bases are less than, equal to, or greater than 1? Remember, equilibrium indicates the extent of a reaction, so you simply have to remember what values of the equilibrium constant would indicate a reaction that favors the reactants. Now, since strong acids and bases ionize completely, they are all equally strong. But since weak acids and bases only partially ionize, they come in different strengths, which is dependent on the degree of ionization. The more ionization, that is, the greater the formation of products, the greater the strength of the weak acid or base. This also means that weak acids and bases will have different values for their equilibrium constants depending on their strengths. The larger the equilibrium constant, the more product favored the reaction is, and the greater the ionization. Okay, so that's it for the review. Now let's get into some new stuff. Here is an acid-base reaction between formic acid and water. Can you write out the products? Take a minute to try and figure it out, since this will be an important skill later on. Remember, the acid donates a proton and the base accepts it. The products must then be formate ion and H3O+. Notice that the products are also composed of a weak acid and a weak base. A weak acid on the reactant side and its weak base form on the product side are called a conjugate pair. So the formic acid and formate ion are a conjugate pair, and the water and H3O+ are a conjugate pair. The only difference between the partners within a conjugate pair is the extra H+. One partner has it, the other doesn't. Also remember that weak acids and bases are always conjugate to weak acids and bases. Here are a few more examples. Pause the video here and see if you can identify the conjugate acid-base pairs and indicate which is the acid and which is the base. Okay, hopefully you were able to figure that out. Remember that all you have to do is follow the proton. Now, since this chapter is about acids and bases, it would not be complete without talking about pH. I'm sure you're all familiar with the pH scale, where low pH values are considered acidic, High pH values are basic, and a pH of 7 is neutral. What pH really refers to is the concentration of H+. It's actually in the name. The P simply means negative log, and H means the concentration of H+. So high concentrations of H+ result in acidic solutions, and low concentrations of H+ result in basic solutions. Here are two acids you saw previously. The graphs show the relative concentrations of H+ for each acid as it ionizes in solution. Equilibrium constants are also given. From the graphs, it should be obvious which acid would result in a more acidic solution. Pro tip, it's the one that ionizes the most and produces the highest concentration of H+. That's the HiO4. You can also reach the same conclusion by looking at the Ka values alone, since larger Ka values means the production of more products, which means more H+, which means more acidic. Here are some more examples. See if you can place these 5 compounds in order from most acidic to least acidic. Alright, so let's talk a bit about water and how it is related to pH. You've seen that the acidity of a solution is related to the concentration of H+, which is determined by a reaction between an acid or a base with water. However, water, even in the absence of another acid or base, can itself ionize. This is called the autoionization of water. Pure water undergoes this reaction on its own, where two waters react to produce one OH- and one H3O+. The ability of a molecule to both accept and donate a proton is called amphiprotic, and the autoionization of water is one example of this amphiprotic behavior. Now this reaction is also an equilibrium reaction, so the equilibrium constant expression can be written like this. Kw is used to indicate that we're talking about water, and since H2O is a liquid, it's not included in the equilibrium constant expression. In pure water at 25 degrees Celsius, the concentration of H+ equals the concentration of OH-, which equals 1 × 10⁻⁷ molar. If this is subbed into the Kw expression, we find that Kw equals 1 × 10⁻14, which indicates very low concentrations of OH- and H+ at equilibrium. What this equation also says is that since the product of the concentration of H+ and the concentration of OH- must always equal Kw, any change in the concentration of H+ will result in a corresponding change in the concentration of OH-, and a change in the concentration of OH- will result in a change in the concentration of H+, so that Kw remains constant. This can be shown using Le Chatelier's principle. If we increase the concentration of H+, the reaction shifts towards the reactants, which must result in a decrease in the concentration of OH- as the reaction moves to re-establish equilibrium. The Kw expression is also used to help determine the pH of basic solutions. Recall that when a base reacts with water, one of the products is OH- rather than an H3O+. I'm using A- here to represent a generic base and HA to represent a generic acid. To determine the pH, we need the concentration of H+, but for these reactions, we only know the concentration of OH-. By using the Kw equation, we can calculate the concentration of H+, and from there, use pH equals the negative log of the concentration of H+ to determine the pH. Okay, now bear with me, I'm taking this one step farther. You now know that the concentration of H+ in pure water is 1 × 10⁻⁷ molar, and that pH equals the negative log of the concentration of H+. So let's bring back the pH scale, and with the information you have, you should now be able to see why pure water is at a neutral pH of 7. If you don't, just plug in the concentration of H+ in pure water into the pH expression, and you will end up with a pH of 7. It is also important to note that on the pH scale, each increase in 1 pH unit corresponds to a change in the concentration of H+ of a factor of 10, since it is a logarithmic scale. So at a pH of 8, the concentration of H+ in solution is 1 × 10⁻⁸ molar, and at a pH of 6, the concentration of H+ is 1 × 10⁻⁶ molar. Two more quick concepts and then we're done. Okay, so weak acids have varying strengths, right? But there are reasons for that. It's not necessarily the fact that the acid form can easily donate a proton, but that the basic form has a tough time accepting a proton. Let me use oxoacids, which are acids that have oxygens in their structure, to help demonstrate this reasoning. When an acid donates a proton, an anionic conjugate base is formed. The negative charge represents an extra electron hanging around that the conjugate base has to deal with. The more that electron can move around the anion, the less likely it is to grab a proton from water, and the more stable it is. Electrons that are more spread out throughout the molecule are called delocalized electrons. In this example, the molecules with a greater number of electronegative oxygen atoms are more able to delocalize the electron. So more oxygens results in a more stable anion, which results in a stronger acid, since the anion is less likely to grab an H+ from water to reform the conjugate acid. Similarly, the electron withdrawing power of a central atom can determine oxoacid strength. In this example, the chlorine is more electron withdrawing or electronegative than bromine, which is more electronegative than iodine. Since the chlorine can remove electron density from the oxygen more readily than bromine or iodine, it helps to delocalize the electron around the molecule and makes the anion more stable. This makes HClO a stronger acid than HBrO, which is stronger than HIO. The last section is on acidic and basic salts. I'll try to keep this short here and we can expand on the ideas in class. Let's say we want to prepare a solution of nitrite in water. Now, we can't simply look in the lab for a bottle of nitrite since bottles of ions can't exist in nature. There needs to be a cation to balance the charge. What we could use is something like sodium nitrite, which is a neutral salt. So what happens when sodium nitrite, or any salt for that matter, dissolves in water? If you are unsure, refer to chapter 4 in your textbook. For our example of sodium nitrite, the answer is that it dissociates or ionizes to Na+ and NO2-. The next question to ask is whether dissolving sodium nitrite in water results in an acidic, basic, or neutral solution. To answer that, you need to know if and how each of the ions, Na+ and NO2- reacts with water. So first, does Na+ react with water? Well, since Na+ is the cation from a strong base, NaOH, that means that it will not react with water. It just moves around in the solution minding its own business. What about NO2-? Well, it's clearly not acidic since it doesn't have any protons to donate. It's going to be either basic or neutral. To be neutral, NO2- would have to be the anion of a strong acid, which it isn't, because that would be NO3-. So NO2- has to be basic. Now, you should recognize from its structure that NO2- is not one of the strong bases, so it must be a weak base. Let's write out a reaction between NO2- and water. Notice that the products are the conjugate acid of nitrite and OH-. The OH- is what ends up making the solution basic. Try to use the same logic to determine whether the following salts are acidic, basic, or neutral. Okay, to quickly summarize, acids and bases can either be strong or weak. Strong acids and bases ionize completely, whereas weak acids and bases do not, and the strengths of weak acids and bases is dependent on their degree of ionization. When a weak acid reacts with water, the products are its conjugate base NH3O+, and when a base reacts with water, the products are its conjugate acid NOH-. Since different weak acids and bases ionize to varying degrees, they will result in different pH values when they are dissolved in solution. The pH is determined by the concentration of H3O+. Water auto-ionizes to produce small amounts of H+ and OH-, and a neutral pH of 7 is based on these concentrations at 25 degrees Celsius. The pH scale is logarithmic, so a change in one pH unit corresponds to a 10-fold change in the concentration of H+. The strength of oxoacids is determined by the stability of the anion, which is determined by its ability to delocalize the electrons around the molecule. When preparing acidic or basic solutions, it is common to use salts, which themselves ionize in solution. These ions may or may not react with water, resulting in acidic, basic, or neutral solutions. So I've covered most of the basics in this video, but there is still much to be done in class. Among other things, we will be calculating the pH of solutions consisting of strong and weak acids and bases, looking at what happens when an acid or base can donate or accept more than one proton, and taking another look at acidic, basic, and neutral salts. That's it for me. I'm Dr. J. Thanks for watching.